So it turns out if you're given 3 segment lengths, you cannot always make a triangle by attaching them at their endpoints. We're going to look at a couple scenarios to help understand this theorem. The first example here, the lengths are going to be 6, 2, and 1. So I've got some noodles that I've actually broken to these lengths. So this one measures 6 inches, this measures 2 inches, and this measures 1 inch. And what we're going to do is we're going to lay the longest one down first, okay? That's what I'm always picturing in my head when I'm doing these. And we're going to attach the 2 shorter sides to the endpoints of that long side. And we're going to think about whether or not they're going to reach. So as you can see, 2 and 1 were definitely too small to reach across 6 inches. Okay, so this is not, we're not going to be able to make a triangle out of that. So you're not going to have noodles at your desk all the time, so what you're going to do is visualize laying the longest one down first, attaching the 2 shorter ones to the end, try and draw it kind of to scale, and ask yourself, will they reach? The math for this is going to be if you put your numbers in order, which I don't write them out in order, but I have to think of them in order when I'm doing this. I'm going to add the 2 shorter ones, okay? To be able to make a triangle, they're going to have to be more than that longest one. And as we just saw, if I add 1 and 2, they're not going to reach across if they're 6 inches away from each other. They're too short. So they're not, their sum was not greater than 6. So did it make a triangle? No, it did not. Alright, let's look at the next example. 5, 2, and 3. So this noodle is 5 inches. This one's 2 inches, and this one's 3 inches. Okay, so for this one, if I picture them attached to 5, my longest segment, can't get them attached. This one's going to be pretty close, so I have to be kind of exact. Okay, are they going to reach? Well, if I put these down so they can reach, they actually do touch, but not until, it's a little hard to work with these, not until they're exactly flat. Okay, there's not going to be enough space here to create a triangle. Alright, so if you take your longest one, lay it down. If you attach your 2 shorter sides, 2 and 3, will they meet? Well, if you close these in, 2 and 3 actually will touch, but not until they lay totally flat because they equaled exactly 5. So did it make a triangle? No. Let's look at the math. Put them in order, 2, 3, 5. Add the 2 shorter ones, 2 plus 3. They're going to have to be not only, do they have to be big enough to touch, but they have to be big enough to create that space to make a triangle. If I add 2 and 3, I got 5. So they were equal, but it was not greater than 5, so that didn't work. All right, we got one more to look at. So we've got 6 here. Whoops, I kind of lost my hairs. 6. All right, so we've got 6, and we've got 4 and 3. That's 2, sorry about that. Okay, here's 4 and 3. So if I attach 4 and 3 to the ends of 6, we're not going to have a problem making a triangle out of those, okay? Because 4 and 3 add up to 7. They're going to be able to reach across 6 and have the extra room to create that space to make a triangle. So again, visualizing it in your head or on a piece of paper, I actually am just picturing it in my head. Laying the longest one down, attaching the 2 shorter pieces, and asking if it's going to make a triangle. 4 and 3, they're going to be able to meet to make a triangle because they add up to 7. So put them in order, 3, 4, 6, add the 2 shorter ones, and that was going to have enough space to create a triangle. Yes, it will make a triangle. You guys, there's the actual, it's called the triangle inequality theorem is the name of this theorem, and it's stated as this: the sum of any 2 sides of a triangle must be greater than the third side. The way the theorem itself is worded, you would be checking 3 different scenarios. I'm going to give it to you this way. I look at it a little differently. I do this shortcut. I say, okay, what do we do here? We laid the longest one down first. We attach the 2 shorter ones. And if their sum, the sum of the 2 shortest sides if their sum is greater than the longest side, you're going to be able to make a triangle. You don't have to check the other two scenarios. If the two shortest ones add up to more than the longest, you're good. You're making a triangle. Guys, my students all the time, they're taking a test. Oh, miss, I don't remember. Is it supposed to be bigger or smaller? You know, there's times where you got to know it. So what I'm doing right here is trying to give you a picture, something you can kind of problem solve. I don't remember this theorem from year to year, but I picture it, just like I showed you here. Lay the longest one down, attach the two shorter ones, does it make a triangle? So let's try an example. This is how it could be worded in a question. Given the three lengths measuring 17, 6, and 9, can you form a triangle by attaching them at their endpoints? Alright, so the first thing I need to do is make sure I know which one's the longest. I'm picturing that one as the one that's solid, not moving. I attach the two shorter ones, 6 and 9, and I'm asking myself, okay, to make a triangle, these two have to reach, and actually more than reach, they're going to have to be more than this one. So 6 plus 9 is 15. I'm not going to be able to make a triangle here. They'll get close, but even when you lay these flat, you know, if you lay down 6 and you lay down 9, you're still going to have 2 inches here, right? That where they're not going to be able to touch. So, my answer is no. And when I'm explaining my answer, basically, I really just have to give the definition of the theorem, right? No, because when I added the two shorter ones, so because the sum of the two shortest sides, because the sum of the two shorter sides was not greater than the longest side. Okay? Pretty simple theorem. Alright, you try one.